Okay, so in the last section, we talked about the reflection of light. And in this section, where ultimately we're going to understand why we can see rainbows, we're going to talk about the refraction of light. You might have noticed that, if you like put a straw into a glass of water and then look at it from the side or from an angle, the straw looks like it's bending as it goes into the water. Of course, we know the straw isn't actually bent, and something about light, for some reason, is not traveling in a straight line from the straw to our eyes, for instance. To help us understand this in section 11.3.1 on refraction, I'm just going to go through the same example that I briefly talked about during class. Right? So imagine that you're like a lifeguard on a beach, and you're standing over here, and there's like a person struggling in the water over here. I guess they're not happy. And you realize you need to get to this person as fast as possible, right? If the goal was to get to this person by covering the shortest distance, of course, you would just take a straight path, right? You would just take a straight line path from wherever you are, across the beach, through the water to this person. But the goal is actually to get there as fast as possible. And the fact of the matter is that you, like most humans, I'm sure, can move across land faster than you can move through the water. Because of that, it's to your advantage not to go in this straight line path, but to actually take two connected straight line paths. First, one that goes, farther over on land, and then takes a less steep angle through the water, right? This part of the path, right here, has a lesser distance through the water than this part, just due to the angle. This part of the path has more time spent on land than this part does. And even though the entire length of this, path formed by these two components, two line segments, is on the whole longer, because the lifeguard can cover the distance on the beach faster, this path will actually be quicker, right? How, far away from this straight line path should you make this point where you, join up the segment on the land and the segment on the water? Well, that depends on your relative speeds through the land and water. If you were able to run, say, infinitely fast across the sand, then you would be trying to just spend as little time in the water as possible. So you would minimize the time in the water, which takes you on this longest path. If you went through these substances at exactly the same speed, then you would take the straight line path, and in between you would do a path that's somewhere in between. Right. So the idea here, which we might call a principle of least time, is that what you're trying to do is not minimize the distance that you're traveling to get from point A to point B, point A to point B, but rather you're trying to minimize the time that it takes to get from point A to point B. And if that's your goal, then the precise path you should take depends on how fast you move as you're going through, any different substances, A and B. Okay. So it turns out that light behaves according to this principle of least time. And in the context of light, this is sometimes called Fermat's principle. So the idea here is that the path that light will actually take will be the one that minimizes the time in between, where it starts and where it ends up. Okay. So, as a little kind of pause before we get back to the idea that light bends, I want to think about this principle from the perspective of, light hitting a mirror. So let's say there's like a ceiling light bulb over here. So there's like a little filament, and it's giving off light. So what does the principle of least time tell us here? Well, of course, for a ray of light to start, say, over here and make it to our eyes, it will take a straight line path, right, doing this. For light to get from the light bulb to our eyes, if we know that one of these rays of light has to bounce off the mirror in the meantime, it will follow one of these paths, which I'm struggling to draw even vaguely appropriately, trying to draw these angles as the same. Right? There we go. And one of the things that's interesting about these kind of straight line paths, when light is just traveling through the air and then bouncing off of things, is that you'll notice that actually all of these paths could be seen to be either obeying a principle of least time or a principle of shortest distance. The straight line path from here to our eye is both the shortest path from here to our eye and the fastest path. And if we say that light has to bounce off the mirror in between when it's emitted and when it hits our eye, then this path is simultaneously the fastest path and the shortest path. So when we think about this principle that we encountered thinking about reflections off a mirror, that the angle of incidence was equal to this angle of reflection, this mathematical relationship comes from both a principle of least time or a principle of shortest distance. Okay? But it turns out, however, light travels at different speeds, through different materials. We were careful to point out that the speed of light in a vacuum, this thing that we called c, and which was very close to 3 times 10 to the 8 meters per second, different materials. This was the speed of light in a vacuum. But when an electromagnetic wave is propagating through something that's not a vacuum, it actually travels slower than this. The reason why it travels slower kind of has to do with the idea that, a wave of light is like an oscillating electric and magnetic field, and that can interact with the electrons and protons in the atoms of a material that it's passing through. And those can then influence back on the light wave itself and cause this electromagnetic radiation to slow down. This slowing down of light in a medium, like air or water or glass, is quantified by what's called the index of refraction. So this index of refraction, which we typically use the letter n for, is defined by the ratio of the speed of light in a vacuum relative to the speed of light through that material. So it's a number which quantifies different materials. Since light is always slower when it's traveling through a material than when it's traveling through a vacuum, we see that this index of refraction has to be bigger than or equal to 1. It's 1 for light in a vacuum, and it's bigger than 1 for light going through anything else. It's a property that characterizes a material. So for instance, for water, N of water is about 1.33 or so, right? So that's to say, light is 1.33 times slower when it goes through water than when it's going through a vacuum. The index of refraction for air, that's actually very close to 1, but it's not quite 1. It's like 1.0003. So it's just like a fraction of a percent slower in air than it is in vacuum. And we could keep writing down these things for other transparent materials. So for instance, the index of refraction for window glass, I think that's about 1.5, 1.5-ish. And the index of refraction for, say, something like a diamond is like 2.4, give or take, right? So light traveling through a diamond goes 2.4 times slower than light traveling through the vacuum of space, and basically 2.4 times slower than through air, and so on. Okay. So what we've just learned, on the one hand, light moves at different speeds through different materials, and I've told you that light obeys not a principle of shortest distance, but a principle of least time. So now we know that if light is traveling at different speeds through different materials, that means we can figure out what path a ray of light will take so that it actually minimizes the time in getting between any 2 points, right? So for instance, if I'm, if I'm standing over here and there's like, I'm standing on a dock and maybe there's like a fish. Great. It's kind of a scarier than usual fish, but whatever. How will light actually travel from, say, a spot on this fish to my eye, right? Well, because light travels faster in air than it does in water, we know actually that it will not take just like, say, a straight line path from me to this fish. Instead, it'll take a path that goes a little bit farther in air and then bends so that there are these 2 straight line segments that it takes, one through the air and one through the water. Right. And the precise details, how far away from this straight line path does the light actually travel, that's given by something that's called Snell's law. So the idea here is, suppose I have a surface, so this is material 1, and this is material 2. This might be, material 1 might be air, material 2 might be water, it might be air and glass, or water and then glass, or something like that. Two different materials where light will travel at different speeds through it. What Snell's law says is that if you look at the angle an incoming beam makes, so we have incoming light over here, and it's coming in with some angle relative to the perpendicular of this surface. So again, I'll call that maybe just theta 1, the angle that the light is making with the surface in material 1. Right? What will happen is that when it passes through this material, it will go at some different angle. So I'll call this theta 2. This is the incoming light, and this is what we might call the refracted light. Okay, and Snell's law gives a precise mathematical relationship between these angles that the light makes with respect to the surface and how fast light can move through these different materials. So Snell's law says the index of refraction in material 1 multiplied by the sine of the angle that it makes on material 1's side of the surface. So n1, index of refraction for this, multiplied by the sine of this angle, is going to be equal to the index of refraction in the other material multiplied by the sine of the angle that it's making over here. Okay. So you can think for a little bit about, well, because of how the sine function looks, sine looks kind of like this, right? That's sine of theta, if this direction is like theta. You can figure out, as you have, say, a smaller index of refraction for material 1 and maybe a bigger index of refraction for material 2, you'll get light that kind of bends like this, going from a bigger angle in the first material to a smaller angle in the second material. I mentioned this in the lecture, but I think it's kind of a fun fact. Let me remind you that Snell's law was named after this person named Snell van Rooyen, who lived in the 1600s. The kind of Latin version of his name was Snellius. And Snell's law was actually, as far as we can tell, first written down by a Persian scientist in 984. So I guess that's how history works. What can you do? All right, so that's how light bends when it goes from one material into another material if light itself travels at different speeds through those materials. Because light obeys a principle of least time, that is, it wants to get from point A to point B, not covering the shortest distance, but covering the fastest path. That means light will bend as it goes from a material where it travels faster into one where it travels slower, or vice versa. Okay. There's one other effect. We've covered reflection, we've covered refraction. There's one other effect that we need to understand in order to figure out why we see the colors of the rainbow when the conditions are just right. And that's something that's called chromatic aberration. Chromatic aberration, right? Chromatic aberration is the idea that actually the speed of light in a material, not in vacuum, but when light is passing through the air or passing through water or something like this, the speed of light in a material depends a tiny amount, just a little bit, a tiny amount on its wavelength. Okay, and that means, among other things, that light will bend by a slightly different angle as it passes from, say, air into water, because the speed of light in both of those materials depends a little bit on the color of light that's coming in. The color of light being itself dependent on the wavelength of the incoming light. Okay, that's why, for instance, that if you shine white light through a prism, you get the colors of the rainbow, right? What's happening is, let's say you're shining white light in like this. White light being itself composed of light of all different colors. Well, the red light will kind of bend a little bit as it goes into the prism. I have a better illustration of this in the lecture notes themselves, where I've done a more careful job drawing this, but here we're just going to get a little sketch. Red light will bend something like this. And bluish light will bend a little bit more at each of these interfaces. Right? And so in between this red light and this blue light, plus maybe a little bit of purple, you get the rest of the colors of the rainbow. Rainbow in between there. Right? Again, the idea is that each color of light has a very slightly different speed, both going through the air and going through, say, this glass prism or going through the water. And that means that according to Snell's law, because remember Snell's law says that, say, n1 sine theta 1, let me write that more neatly, n1 sine theta 1 is equal to n2 sine theta 2. And remember that these n's, n is the speed of light divided by the velocity of light in the material, so speed of light in a vacuum divided by velocity of light, speed of light in the material. Well, if this depends a little bit on wavelength, then the relationship between the incoming angle and the refracted angle will also depend on the wavelength. So if I make this a function of the wavelength, then the angle here depends a little bit on the wavelength. Okay. It's called chromatic aberration, by the way, because during the Renaissance, it got in the way of making really good lenses. A lens is, say, like a carefully shaped piece of glass that is meant to take, say, parallel incoming rays of light and focus them down to a point, so that at some distance away from the lens, all of these light rays converge properly. For instance, maybe the lenses in our eye take light that's coming in and focus them to a spot on our retinas. And if our lenses in our eyes aren't quite right, we can wear glasses or contacts that act to change exactly where that focus spot is, so that it lines up with the back of our eyes. Okay. Well, this is all well and good, but if light bends by a different amount depending on its wavelength, then actually the focus spot of these lenses will depend a little bit on precisely what the wavelength of incoming light is. So the focus spot of a lens will be perfect for some wavelengths of light and off for other wavelengths of light. And so it's called chromatic aberration, even though there's nothing, let's say, inherently wrong with it. Okay, knowing about these three key things, the reflection of light, the refraction of light as it moves from one medium to another, and this idea that the amount of refraction depends on the wavelength of light, we can actually now understand what we're looking at when we see a rainbow. So first, let's take a look at, let's say, what happens when a beam of incoming sunlight hits a spherical rain droplet, right? So let's draw I keep forgetting that I can actually change colors over here. We've got a happy sun throwing off some rays, and I'm going to have some of that white light, not to scale, approach this raindrop. Okay, so when this white light, again, just a name for a combination of all of the colors of light moving towards this raindrop, when white light is approaching, what's going to happen when it hits? Well, some white light will be reflected off of this raindrop, right? And so it will make an equal angle with wherever it's striking this raindrop. Okay, so some amount of white light bounces off. Other amounts of light will pass into the droplet, but it will be refracted, right? Because it'll be refracted because the speed of light in water is less than the speed of light in air. Okay, so now we've got, say, some red light moving like this, and maybe some purple light that gets bent a little bit more. Okay, what happens when these bits of light hit this side of the rain droplet? Well, some amount of it is going to reflect off of the raindrop, and some amount of it is going to refract again. So it's going to pass back out of the raindrop into the air. Okay, and then at this surface, again, some amount of it is going to bounce off the raindrop, and some amount of it is going to pass through, bending a little bit as it goes back from the water to the air. Okay, what's happening with this red droplet? The same basic thing. When it hits this side of the water droplet, the red light, some of it will refract back into the air, and some amount of it will reflect off the surface of the water drop, going over here. When it hits this surface, some of it will reflect again, and some amount of it will refract back into the air. Okay, so we have these violet rays of light, violet rays of light, and these red rays of light going off at slightly different angles, because at each of these refractions, the purple light will bend a little bit differently than the red light will. Okay, so if we're standing, down here, amazing. Some of these different colors of light might hit us. And to give you a sense of what I mean by these different colors of light bend by a very different, or by a slightly different amount, the angle in between the incoming white light and this first kind of violet outgoing ray of light is about 40 degrees. And the angle in between the incoming white light and the outgoing ray of red light is about 42 degrees. So about 2 degrees of angular difference is the difference between the entire range of the visible spectrum, basically. Okay, so this is essentially enough for us to understand what we're seeing when we see a rainbow. So if I kind of start my sketch over again, I'm going to have a rain cloud over here, with incoming white light from the sun. And the rain cloud, there's going to be a bunch of these little droplets of rain. And off of each of these drops of rain, as white light comes from over here and strikes each of these raindrops, there's going to be like this whole process of light bouncing around inside each droplet, with violet light coming off at a 40-degree angle, red light coming off at a 42-degree angle, and all the other colors of the rainbow in between. Right? So each of these drops of rain have this kind of feature. So if there's someone standing on the ground over here where the sun is behind them, then there's a chance for sun coming from behind them to strike one of these raindrops, and where the light makes a 40-degree angle, the person will see any of these purple drops, and where the light makes a 42-degree angle, none of this is to scale, just because I'm not a good enough artist, a 42-degree angle, any of the drops where you've got that red will strike the person's eye. And in fact, they'll see this whole arc. Any droplet at this correct angle relative to the person will be sending red light into their eyes. Any droplet at this 40-degree angle will be sending purple light or violet light into this person's eyes. And in between, you'll get all the other colors of the rainbow. Right? So the center of the rainbow will be directly opposite where the sun is, and everywhere where there's a raindrop that's capable of scattering light in this way back into the person's eyes at the right angle, the person will see that as like this beautiful arc of color. Most of the time, of course, we're standing on the ground, and so these rainbows have to stop somewhere. But in fact, if you're skydiving, or if you're extremely lucky and you're in a plane, sometimes the conditions are just right for you to see not just one of these semicircular arcs, but actually the entire circle of a full rainbow, which there's a link to a YouTube video of someone skydiving and seeing this in the lecture notes. It's just remarkable. Great. So that is what we're actually seeing when we're looking at a rainbow. What we're fundamentally seeing is the sun is somewhere behind us, white light is coming in and striking basically spherical drops of water being deposited by a cloud. And because light not only bends as it goes from one material to another, but bends at slightly different angles when the light has different wavelengths, different colors of light that are originally coming in to hit the droplet get split a little bit. Just like as if these drops of water were acting as tiny prisms. And then any droplet of water that's making the right angle between the water, the sun, and us will appear as a part of a circular arc of color up in the sky. Okay, so that's how rainbows work, and in the last section, we'll talk about why the sky is blue.